The world is unable to produce enough energy or resources to be sustainable in the far future. The solution will be to utilize space to deliver these needs. Unlimited energy and resources live beyond our world. If we want to cure climate change and habitat loss, we cannot rely on human behavior. Instead, we must engineer our way out of the problems we've created. This is the story of how one energy technology and a dream to mine asteroids might one day change the world.
When I was a little girl, I was a stargazer, and I was in awe of the sun that powered the Earth. Space-based solar power is a technology you probably never heard of. It was invented in the 1970s by Peter Glaser. Back then, it was a dream, because the cost was enormous. A revolution in science is about to change that.
Space-based solar power, or space solar for short, is the concept that we collect the abundant sunlight in space and send it wirelessly to the Earth. It can be collected in a number of ways, either with solar cells or with some kind of heat engine, or even perhaps with a laser that's pumped directly by sunlight. The energy is sent without wires, using optical, electromagnetic waves, lasers, or microwaves, millimeter waves, all in the radio spectrum. And then these would be received on Earth. You might ask, well, why would we do this? We can get the sunlight on the ground without a satellite. The only problem is you cannot do that at night. You can't do it if it's cloudy. And if you are trying to use solar energy, you need to store it to get through these times. And if you have a month's worth of clouds, that's a lot of storage. So the advantage of collecting it in space not only means you have it continuously 24/7, but an advantage you get from it that is unavailable through any other energy source is the prospect of being able to distribute it globally, to use satellite coverage to send the energy where it's needed. So this represents a source that's not only clean, but it's constant, globally distributable, and it's effectively unlimited. The sun is the closest thing we have in our solar system to an infinite source of energy. The sunlight is brighter than anywhere on Earth. It's never cloudy, it's never rainy, and in the right orbit, it's not even really nighttime for any appreciable amount of the time. If you're in geosynchronous orbit, a satellite is going to be in sunlight more than 99% of the time, and obviously with multiple satellites, you could always ensure that there's going to be a satellite that will be in sunlight. So by taking advantage of this very bright, uninterrupted sunlight, you now have a continuous source of energy. You don't need as much storage, and you can, even more importantly, send that anywhere you need it in the world. You don't need to have power infrastructure. You can set up a receiving station in the middle of the desert, in the middle of the wilderness, send energy directly from space to that. That's not a capability that we have right now. So the prospect is quite attractive.
Space-based solar power is dependent on three main parts. The three parts are solar collectors, a transmitter, and a receiver. The solar collectors are often solar photovoltaics. The transmitter would be a magnetron or a laser. This would send millimeter waves or lasers towards a receiver. The receiver could be a rectenna, a very large receiver underwater or buried in the ground, or a laser sail used to propel spacecraft. Valerie traveled to Japan to find out more.
My name is Shinohara of Kyoto University's professor. From my student time, my research topic is solar power satellite and wireless power transfer via microwave. So I belong to the electronical engineering department of Kyoto University, and our technology mainly wireless power transfer via microwave. Not only the solar cell or rockets or the other space technology, but consider microwave power transfer, wireless power transfer is one of the most important technology towards the solar power satellite. So as you know, in Japan, we don't have enough budget to develop the space technology. So of course we have a rocket technology, for example, H2 or the other Japanese rocket. But this technology is unfortunately poor compared to the NASA or ESA or the other technology. So in Japan, to develop the space-based solar power satellite, we have to launch very huge amount of the material, solar cell, antenna, or the other. So rocket technology is one of the key technology to realize the solar power satellite. But in Japan, unfortunately, we don't have enough rocket to launch very large materials.
Mm-hmm. Can you please tell me what is this one?
So this is a retro-directed phased array system. This is our facility for students in my university. Mm-hmm. And from each antenna we can control the phase of the microwave power. And
Professor Shinohara went on to explain how retro-directed phased arrays use interference to redirect a beam of energy. This means there is no need to physically change the direction of the transmitter.
Critics of space-based solar power point out it isn't efficient. The number of conversions of energy from light to rays to electricity seem wasteful.
What about efficiency? Does it matter?
The efficiency matters for viability, but perhaps less than you would think, and it's actually sort of a secondary concern. One thing that often gets lost sight of is because most of the cost is likely to be in putting the hardware in space, the satellite that actually does the conversion, it's more important to have high watts per kilogram, which is to say you want to be able to put down a lot of power per unit of mass that you put in space. Now, if you have high efficiency, that probably means your specific power, your watts per kilogram, will also be high. But even if you were actually not that efficient, if you could do it with very lightweight hardware, that might prove decisive in making the economic case.
Back in the 1960s, Most launches used rockets that went up and never came back. Their remnants burnt up in the atmosphere. Elon Musk and SpaceX changed all that. The best versions of space-based solar power will need to be in GEO orbit at 36,000 kilometers from Earth. These will provide nearly a continuous stream of energy. To get these large systems economically into space requires the lowest cost transport. It's not surprising that systems other than rockets are being developed. Another technology to help space-based solar power into orbit is the space elevator. The idea is to move payloads up and down a light but strong system of cables that extend into space. Once in space, small spacecraft will dock and move these payloads to higher orbit.
Are the photovoltaic panels the same as I might put on a house or in a field?
The photovoltaics that are used in space are different than the ones you might stick on the roof of your house. The reason for that is the spectrum in space is a little bit different. As we know, the sky is blue, and that's because the blue components of the sunlight get scattered in the atmosphere. So it's okay to have a solar panel on the ground that is less receptive to the blue light. In space, you want to take full advantage of that. You've got, as we've discussed, this brighter sunlight in space. So photovoltaics for space often typically have multiple layers to get the most out of each section of the spectrum. Now, the photovoltaics we use in space are also a lot more expensive than the ones we use on the ground. If you buy a solar panel at the hardware store, it's usually going to be a silicon solar panel, as these are cheap and mass-produced. For space, we use what are called triple junction or quadruple junction solar cells that really get the most out of each section of spectrum. So for solar power satellites, because we're going to be making potentially huge areas of these photovoltaics for the solar panels, you would have to consider carefully what are the best materials to use, just because of the quantity needed and because of the cost considerations.
I have also heard that some designs incorporate mirrors to deflect their sunlight onto the photovoltaics in space. What's the motivation behind this?
There's a motivation for space solar to use large reflective surfaces or mirrors to collect and concentrate sunlight. One of the reasons for this is you can make mirrors very, very lightweight. It can just be a really thin sheet of mylar or Kapton or reflective material, and that's a lot lighter than a photovoltaic. So you'd prefer to maybe launch 10 times as many mirrors and like a tenth of as much photovoltaics just to help keep the mass down.
And I believe there are other ways to collect the energy of the sun.
There are other ways to collect energy, other options besides photovoltaics. You could use a heat engine or even a laser that's pumped directly by sunlight.
To make this possible, though, these systems must be very large. Whether rockets, space planes, or space elevators are used, there is a need to move a lot of mass in small spaces.
How large would the structures have to be, and how would they get into space?
Because most of the concepts for space solar present structures in space that would be of unprecedented size, the way that they would be assembled has to be carefully considered. Right now, with the exception of the International Space Station, all of our satellites have to be crammed somehow into a single launch on a payload, inside a payload fairing of a single rocket. Because for space solar, you're probably going to want to collect a lot of sunlight that would require a large area, and if you're using microwave transmission, you also need a stupendously large microwave antenna in most cases. There's going to be a need for assembling things in space. To do this, you could use robotics. You could also use astronauts, as was envisioned in the 1970s, but the problem with astronauts is they need to eat, they need to sleep, got to keep them alive. Robots have much less stringent requirements for such things. So robotic assembly is really attractive. There's also been discussion of doing 3D printing, additive manufacturing for these large satellites, maybe even using materials that we get from the moon or from asteroids to minimize the amount of mass that is to be sent into space.
Each payload a rocket or an elevator houses needs folding up, and once in space, unfurling. Valerie visited Oxford Space Systems to find out about how to solve this, inspired by Japanese origami.
My name is Michael Loworth and I work here at Oxford Space Systems. I'm the Business Development Manager. So my role is to be one of the outward facing people, talking to industry and to other people who would be interested to find out who we are and what we do. And Oxford Space Systems is quite a small SME. So we are a small company, started in 2013. We are venture capital backed, and our whole remit is to use smart, intelligent materials and understanding to make deployable structures for space, somewhat like this.
Oh, wow, that's impressive. So in space, right?
Yes, so this is deployed quite quickly, and in space we control it, but this is carbon fibre. So most people know carbon fibre is that solid stuff that you have making Formula 1 cars, for example. But what we've worked out is we've looked at the chemistry and made the layup so that we can then fold that up without it shattering. So we can stow it nice and small, which is something you need to do in space. To get this into space, you need to put it onto a rocket launcher. So you want to have it nice and small. You want it as light as possible so that it's as low cost as possible to put it into space. Once in space, you then want to deploy it. So you have these large solar arrays, these large antennas, and all of these different structures that you need on your satellite, taking up all of that space to then get power, to transmit your communications, or to do whatever your payload needs to do in orbit.
Do you think it would be possible to unfold solar panels with the origami method?
Yes, so if you look at our website and look at us online, we've done quite a lot of different structures where we compress them right down and deploy them out.
So solar panels will be also possible?
Now, solar panels we could do in a couple of different ways. We could either do that the traditional way on wings, and we've done that with some development where we've been developing highly articulate two-axis deployable structures, so you can deploy your arrays out and then twist them up, down, round to really point towards the sun or whatever else you need to do. We've then got a really blue skies idea at the moment where rather than just deploying an antenna from a satellite, we deploy the whole satellite. So you get this box, you launch it up, and then the whole box unfolds and unfolds into this nice big flat structure. So you can have your solar array on the back side, you can have thicker panels with your computer, your AOCS systems in there, and you can then on the other side have your array for communications or for SAR imagery or for whatever the application is. And that's a real blue skies forward thinking. But in between we've got structures. Should I go and get that and come back and show you?
I think, yeah.
See a structure that's nice and flat packed, just like you're talking about. But in this instance, what we've done is we can unfold it, and here, this is designed as a parabolic antenna. But you can see how with the same sort of panel concept, we can mount something like solar arrays on there and start to use this in a number of different ways. So we can use this as a structure to mount other systems on top of that.
Yeah, so you'll have infrastructure.
Yes, so this is the sort of infrastructure we can do. So it doesn't have to be circular. In this instance, we've made it circular for the application we're looking at. But it starts to give you an idea of how we can fold up and make these structures very, very small. So this is quite an art. I'm not used to doing this. Yeah, so it's an opportunity where we can fold down, and it gives you a great example of the kind of flexibility that origami starts to give you. So this is a concept that we worked with Oxford University with, and it's using the principles of origami engineering to understand the angles and the precision of how to put this together.
Teach me how to do it.
Yes, if you take hold of these, well, yeah, 2 points there,
Thank you.
and if you push together and pull up, you'll see the structure wants to deploy out. And here you can see how this is designed to have this very nice parabolic shape. Now what we found was for space applications, it's too strong, heavier structure. We can slim this right down. But it's this kind of Mobility One concept that has driven a lot of our other design process. So when we've looked at then doing some larger antennas, say to put it apart and it'll just come down. So, we've used this same kind of principle so that you can have one motor driving a massive structure that opens out 2, 3, maybe even 15 meters in diameter. But by knowing where these 2 points are, you know where the whole system is. And you can then add redundancy by not just powering 1 point, but powering 2, 3 or more points. And you then have the flexibility to develop that concept more and more. But space is all about trying to get a nice, simple idea and just small, bite-sized evolutions, just bringing it on, bringing it together. We're trying to make sure it's a bit more innovative. Astrotube Max, and we have Astrotube. So Astrotube is carbon fibre. So we all know carbon fibre, got some there, nice, solid, strong. Yeah, it's not a magic trick, it is really there. That carbon fibre is normally something that will shatter if you try and bend it. But we've worked and we've looked at how we can make that into a structure that can be deployed, so we can start to flex that structure around. So what we've done, and the fun one is this one I'll show you again, doing it that way. Now in space, you don't want to make that kind of big flick motion because you'll unsteady your satellite. Instead what you want to do is you want to use some actuators, some light controlled reliable motors that can control that deployment slowly, and that's what we've done here. Let me just turn it on. Plug it in. Yep. So here, if you look down here, and I'll just turn this around, you can see a cassette, and that's got this Astrotube material. Further round, you can see a redundant motor system which goes into these holes, and they all serve to feed this through. So if I undo the top and take this down, what you'll see inside is this material pushing us up and up. Now what that does is that allows us to take this material, which is really strong actually, but depending on how we develop it, may not be as strong torsionally, into something here that is solid. And we've got these carbon fibre tubes, telescopic tubes being driven out, and that means that we're we've developed a structure that can sustain a lot more force, a lot larger structures. So something like this could be used to attach flexible solar arrays, for example, and just like the banner back there, we can drive your solar arrays out for the length of a football field or however long you need. At the moment we make these to about 10 metres, but we're looking at 15, 20 metres and longer solutions. Technically, that motor is a defined unit. Then it's about how much material we have and how long a telescopic boom we put it into.
How much do you use now?
Pardon?
How much material do you use now? I mean, how long is it today?
This will go up to the ceiling, so this is about 3 metres, I think. 3.5 meters
What
actually.
about the Asteroid you used in 2016?
So 2016, that was just this material, and that was 1.5 meters. So 1.5 meters deployed. I'm going to stop it before I damage the ceiling.
Yeah, sure.
Oxford Space Systems is a space tech business, and what we're doing is developing a new generation of what we call deployable structures for spacecraft. One of the big restrictions on the industry is stowage volume. We've got to fit every bit of technology we want to get into space in the small pointed bit of a rocket. Once in space, the structures deploy to bring the satellite to life. Great examples are solar panels to provide electricity and large antennas that unfurl to communicate to the Earth. The art of designing these deployable structures is what Oxford Space Systems is all about. What sets us apart is that we're designing and developing our own new generation of materials that can survive the space environment. It can literally cost tens of millions, if not even hundreds of millions, to develop new products for space. But the prize is there if we get it right.
The advantage of large-scale space-based solar power is that it's easy to redirect because it requires no moving parts. One could set up ground stations anywhere on Earth, including out at sea, and provide free energy 24/7. Choosing the right place, though, is critical to the success of the system because they require large areas away from populated zones. Once constructed, though, they can be built so they are invisible and have no impact on the natural world.
I traveled to Easter Island, one of the remotest places on Earth, to find out more about the island and how it keeps the lights on. In 2016, the diesel generators on Rapa Nui failed to meet the demand. So what are your thoughts about this?
Yeah, I mean, energy is a problem here on Easter Island because the moment we depend on diesel that's transported from South America over to here, kept in tanks and then distributed to the generators, that, as you say, sometimes the demand on those generators is simply too great. And so I think, up to a certain point, they had to increase the amount of generators, but everyone here is very clear that the island should be making more use of the natural energy that surrounds us. Up until very recently, that's always been thought that we could do more with solar panels in order to get much of this sun that we get on a daily basis here. Wave power as well, we've got breaking waves around this island the whole time. Wind as well, there's an island with quite a lot of wind, and so we felt, or I've always felt at least, that the island could and should do much more. But if, as you say, this new technology is out there and it doesn't actually require large windmills or solar panels to be put all over the island, then I think, of course, the island would always be interested in... The beauty of Easter Island is it's a small population. It's only about 8,000 people that live here, a couple of thousand tourists on the island at any one time. It means that you don't really need energy for more than about 10,000 people at any one moment. And so I've always thought the island would be a very good place almost to test some of these things, and a very good example to say, look, Easter Island is completely self-sufficient. I think Chile, this is something that Chile, could have looked at, certainly in the past, of using Easter Island as an example of how they, were invested in green energy.
The future of space-based solar power isn't limited to providing energy for the Earth. There is a greater reason for deploying space-based solar power. It also started with a dream. Carl Sagan, the Canadian cosmologist, promoted the idea of a solar sail on the Johnny Carson show in 1976. It would not be until the Japanese launched Icaros, proving the concept. This, though, was only a beginning. New kinds of directed power beams and laser wafer sails will open up the solar system to us. These will have printed circuits on them to examine asteroids. The flight time of these could be days rather than months if powered by lasers using laser sails. With that in mind, Valerie went to meet Mitch Hunter-Scullion, one of the most important people in the world of asteroid mining.
So I'm Mitch Hunter-Skillion, I'm the CEO and founder of Asteroid Mining Corporation. As you can probably guess, Asteroid Mining Corporation, probably clues in the name. We are a company which is designed from the offset to go and mine asteroids. Obviously, that's not something which is happening today. It's an aspirational business name, and we've been working for 7 years now to kind of start pushing asteroid mining as a real business. Obviously, 2016, this was considered to be very much science fiction nonsense. But I think one of the things we've done very well is to actually start to bring it into the nearer term to provide a viable opportunity, a viable economic incentive for asteroid mining, and to really start to make people believe that it is something which will be possible in the near term.
So everything started from a dream?
Everything has to start from a dream.
Why should the world invest in asteroid mining?
Well, asteroid mining has the opportunity to radically alter the global economy forever. Obviously, Earth is a very large planet. It's very big. It's the only planet we've ever known. And we all like to think that it's, it's infinite. But it's not. The resources of Earth are finite. Whereas on asteroids, there are over 4 million asteroids in our solar system. The total density of those asteroids are equivalent to a planet in themselves, if not more. So what you need to look at asteroids as is essentially a failed planetary remnant. But the benefit is, because they didn't form into a planet, they are essentially the building blocks of the planets. So the things that we cannot access on Earth, things like dense heavy metals that sunk into the crust during the early formation of the solar system, we can get on the surface of asteroids, because they would be present on our planet, on the surface, if we didn't have the planet that we have, because the Earth got hit by so many objects in the early bombardment phase that the Earth started to gain mass, it started to spin, that heated up the core of the Earth, that caused kind of geodynamics and thermodynamics. So this led to the Earth being a very different place. But asteroids are the same things. They're just in space and they're accessible. You don't need to dig 20 kilometres down to try and get some of these metals. You can find them on the surface. And when you're talking about particularly things like platinum group metals, there is so much of them on asteroids that it presents arguably one of the greatest economic opportunities in human history.
If you mine 20 tons of platinum, how much would your company earn?
So 20 tons of platinum at current Earth market price is approximately £500 million. So we play a game where we try to make our mission cost less than that so we can turn a profit. How much less than that is debatable, because obviously space is not cheap. It's an expensive domain to be operating in. But I will say that mining on asteroids, from our analysis, doesn't seem to be any more expensive than mining on Earth. When you look at an open cast pit mine on Earth, an open cast pit platinum mine on Earth, then you're looking at something in the region of a 20-year development cycle. You're looking at a cost of approximately $4 billion. And you're probably looking at, profit, but not a huge amount of profit. Whereas if I could convince a mining company to give me $4 billion, then I could start delivering hundreds of tons of platinum down from space. Obviously, asteroids are interesting for various purposes. You've got metallic asteroids which contain platinum group metals, iron and nickel, building blocks of steel, building blocks of the future, kind of space infrastructure. But you've also got kind of carbonaceous and silicaceous asteroids which have quite a high water content as well. Water being incredibly useful both for spacecraft propellant and also for keeping astronauts alive, and air, water, oxygen, life support systems, even things like kind of hydroponic agriculture in space. This is all incredibly important for the expansion of humanity out into the solar system.
Can you tell me about extra benefits of asteroid mining?
Oh yeah, well, the benefits of asteroid mining are not really going to be felt in space for probably a few decades. I would say that the most immediate benefit of asteroid mining is that it's going to be used on Earth. So the resources, particularly the platinum group metals that we're going to be getting in space, we're going to send down to Earth. Those resources are going to be used to essentially transition to a hydrogen-based economy.
The European Space Agency suggested laser propulsion for asteroid mining. Why would this be beneficial?
Laser propulsion is a very interesting one because with laser propulsion you don't have to send up propellant from Earth in the same way. So obviously you have to get into Earth orbit, but then as soon as you're out of the atmosphere of Earth you don't have atmospheric drag. So if you could have a kind of a laser propulsion technology which would allow you to be able to basically kind of propel yourself without mass, well, essentially massless propellant, if you will. Essentially using electricity and converting electricity into lasers, into light, and then using that to propel your spacecraft. That would be a huge transformation in the space industry, because that would mean that destinations which are currently too expensive to access would become more readily accessible. Places that we would like to go to but can't afford to would become accessible, would become open to a new economic frontier of opportunity. So laser propulsion is very, very interesting. It's going to be, I'm sure, over the coming decades, a very important part of the emerging industry. Compare it to steam trains. Steam trains were great for 150 years, and after a certain point steam trains became a novelty. I imagine chemical propulsion will probably go a similar way. There will come a point where, you know, using chemicals to fire your rocket into space may well become outdated. But we're not quite there yet, unfortunately. This is the Asteroid Prospecting Satellite 1. So we are looking to launch this within the next 18 to 24 months. If you can imagine this, but the size of perhaps a small bus, then that's what we're working with. This is essentially the version 1 of what we will be sending to asteroids one day in order to take those powdered asteroidal samples, and then we will be able to essentially put that into a much larger version of this satellite, but on an asteroid, and then start to filter out tons and tons of metal in order to identify where the precious metals are, separate out the stuff we don't want, and only be bringing back the most valuable resources from space.
Mitch went on to show us his amazing collection of meteorites.
Do you think we'll see asteroid mining in our lifetime?
So I would believe that asteroid mining is absolutely the future. I wouldn't be doing my job if I didn't. I would like to think that if we are going to expand our economy, you know, there's lots of talk at the minute about limits to growth, about, you know, economies can only grow so far. After a certain point, economies will start to contract. At the moment, we're doing untold damage to the environment just with the current model. That has to change. It must change. If it doesn't change, we're going to enter a period of protracted decline, and, you know, some more kind of doom mongers within the kind of global economy might say that if we don't start to change, then we might be looking at a very different and slightly bleaker, if not incredibly bleaker, viewpoint. So I think that asteroid mining is one of the key opportunities for the future. You do not have limits to growth in space. You do not have geographic limitations. You do not have national boundaries in space. There is an enormous amount of land in space. There's an enormous amount of opportunity, and it's a new frontier. Perhaps it's the last frontier. Perhaps it's the final place that we will go and we will start to learn more about ourselves. But once we're out there, you can't come back. You know, we didn't leave the caves and go back into the caves. We left the caves and spread ourselves around the world. And we're going to leave this planet one day and we're going to spread ourselves throughout the solar system. This will happen. This is the future.
Have a cut to home and a city home.
Do you really think that asteroid mining in the future?
Oh no, it's the present.
The present?
It's happening now. I would like to think that we're going to make it happen sooner rather than later. So it's definitely getting there. Definitely getting there.
A couple of years, perhaps?
Yeah, not too long.
Yeah.
It'll flash by in a blink for now.
Mm-hmm.
We've been going for 7 years, so it's taken us 7 years to get here, and 7 years to be in an asteroid, I think. Oh yeah, the future's definitely up there. You can almost see it, look.
Where do you see an asteroid?
Oh, there's one right there. Do you not see it? It's just behind that building.
So do you think it is a future, Mitch?
Yes, absolutely. I mean, when you think the asteroids are only really just up there.
The most dangerous threat to human life on Earth isn't climate change or nuclear war. It is, of course, supervolcanoes and large, fast asteroid and comet strikes. We cannot stop supervolcanoes. All scientists agree an asteroid strike will happen. It's not a matter of if, but when. So how do we stop them?
This is a special announcement from the BBC World Service from London. Breaking news. A large meteorite has exploded off the coast of Portugal. Part of the ocean was vaporized, sending shockwaves and boiling water across nearby coastlines. Hot air and poison gases have also been reported. Minor tsunamis are traveling towards the eastern seaboard of America. Several ships have been vaporized by the blast. Further reports will follow shortly.
The applications for space-based solar power extends much further. It could also provide a planetary defense system. D-STAR, or Directed Energy System for Targeting Asteroids and Exploration, is a proposal by Professor Lubin. This would utilize space-based solar power and link it to a highly focused laser beam. This is like the laser weapons carried aboard US aircraft carriers. Early warning probes in the asteroid belt would detect rogue threats. A system called D-Starlight, a flyby laser system, could be used to vaporize part of them. This would change their trajectory. Alternatively, D-Star in orbit around Earth could be used to redirect their path. This also brings the possibility of capturing a large asteroid for mining purposes.
How long will it be before we have commercial space-based solar power beaming energy to Earth? The Chinese might have a workable system by 2030. In 2023, Caltech in the USA used the demonstrator rig to harvest solar energy and beam it back to Earth. The platform in low Earth orbit was a flexible, lightweight microwave transmitter. Controlled by custom electronic chips, it was a huge investment. Called Maple, it was launched on January 3rd atop of SpaceX Falcon 9. The team leader, Professor Ali Hajimiri, announced that the beam was detected at Caltech. It paves the way for larger systems and new investments.